Hi. This will be the third and final recording or section of our Mariab Human Anatomy and Physiology chapter 26 discussion. This chapter is about fluid, electrolyte, and pH balance. And we've covered those first two topics, and now we're going to have a nice succinct description of pH balance. pH is a measure or an expression of the hydrogen ion concentration of a solution. And when I use those brackets around a symbol like this, it means just concentration. So if we have a lower pH, annoyingly maybe, it means a higher hydrogen ion concentration. And we call that condition an acidic condition. A higher pH means a lower hydrogen ion concentration or a more alkaline condition. So that's just the definition of pH. It's the negative log of hydrogen ion concentration, so it moves in the opposite direction as the absolute concentration. All right. Acids, for our purposes, we're going to use a very simple definition of acids and bases. Acids we're going to think of as chemicals that release hydrogen ions into solution and increase the concentration, and a base as a chemical that can mop up or take up hydrogen ion concentrations, hydrogen ions from solution, lowering its concentration. Now, the blood pH is very tightly regulated because virtually every functional element within a cell and in different parts of the body besides within cells is dependent on proteins, membrane transporters, enzymes, cytoskeleton, connective tissue proteins. All these proteins depend on the proper pH for their function. They just completely change in their properties utterly if the pH isn't maintained. So we keep the pH around 7.4. That's the textbook neutral pH value of the body fluids. A little more acidic, probably 7.0 in the cytoplasm of the cells. If we get away from that even a little bit, if the pH goes up, in other words, hydrogen ion concentration goes down to say 7.45 or above, then that's called an alkalosis, and an acidosis is defined as a drop in pH below 7.35. So it doesn't take much to be considered a clinically important situation. Typically, there's an excess production or accumulation of hydrogen ions in the body each day. Those hydrogen ions are coming from digestion of foods, certain foods, especially phosphorylated proteins. Couldn't get that out. Other digestive processes lead to hydrogen ion release. Hydrogen ions are produced during metabolism. The end of the mitochondrial electron transport system, or in the process of the electron transport system, we have hydrogen ions being produced. Lactic acid. Lactic acid is produced during anaerobic respiration by cells. They oxidize glucose to form pyruvic acid, and then they must ferment that to lactic acid in the absence of oxygen. And finally, keto acids. Sometimes there are maybe ketone bodies produced by the liver when there's insufficient access to carbohydrates, either because of malnutrition or starvation, or because there's no insulin to allow the cells to take up the carbs. So we have ketoacidosis potentially. What to do about hydrogen ions? There are three kind of stepwise things that happen to deal with those hydrogen ions so that they don't change the pH appreciably in our body. The first is chemical buffers. That's the immediate thing that happens. Chemical buffers are chemicals that prevent the changes in pH by taking up or releasing hydrogen ions as they appear or disappear. But they're not a good strategy for long-term regulation. They have a finite capacity. If we continue to produce hydrogen ions and all we have to deal with is a chemical buffer, it would very soon be saturated, and we'd have just a huge buildup of hydrogen ion concentration and a terrible pH imbalance. Okay, so we got to have other things, and we have two organ systems that will represent physiologic mechanisms for dealing with the pH balance requirements of the body. The respiratory system controls the pH by changing the ventilation rate. Respiratory control centers in the brain will adjust the ventilation rate based on pH of the blood. And that gives us a good few minutes of time's worth of of regulation of pH. The kidneys' job is to control the pH over the long term to make sure that the other systems are in the middle of their range of function. We mainly want the respiratory system, obviously, to give us the right amount of oxygen intake into the body and getting rid of the right amount of CO2. So just one more thing about chemical buffers. What are those chemical buffers that we're talking about? Chemical buffer, again, is a chemical or a mixture of chemicals that can take up hydrogen ions if they begin to rise, if the pH drops, or they can release hydrogen ions if the pH rises or the concentration goes down. Keep that pH is relatively constant. Plasma proteins are an important buffer. These long chains of amino acids contain side groups. The side chains of the amino acids have functional groups that can act as acids or bases, meaning they can take up or release hydrogen ions. I said those in the opposite order I should have. They have a high buffering capacity because there's a lot of plasma proteins. There's a lot of hemoglobin. I'm sneaking that in there because it's in the plasma, even though it's intracellular in the red blood cells, but they can buffer a lot of hydrogen ions. Bicarbonate buffer system. That's an important buffer system of the extracellular fluid. The way it works is there's a significant amount of bicarbonate ion in the blood, and that's maintained by the kidneys, 24 millimolar. If we add some hydrogen ions, as we typically do each day, into the plasma, into the extracellular fluid, it will combine with bicarbonate ion. It will be buffered, producing carbonic acid. So those hydrogen ions are no longer in solution. They're going to be converted into carbonic acid. If the hydrogen ion concentration goes down, if we had the opposite condition, an alkalosis, carbonic acid could dissociate and will dissociate and release hydrogen ions into the solution to maintain pH, keeps it from changing. The intracellular situation is very similar, just a little different. There's a lot of protein inside the cells which buffer in the same way that plasma proteins do, and technically hemoglobin is an intracellular buffer. But the counterpart to bicarbonate ion inside cells is hydrogen phosphate. There's not a significant amount of bicarbonate inside the cells, but there is hydrogen phosphate, which can act as a weak base and take up hydrogen ions. Or once we form dihydrogen phosphate and there's an absence of hydrogen ions, it can then release the hydrogen ions to produce hydrogen phosphate once again. So we have this back and forth reaction potential to get rid of or take up hydrogen ions. The respiratory system, now we're looking at the physiologic regulation of pH. The respiratory system, how does that help us with pH balance? Well, we've already seen that bicarbonate in the plasma can buffer hydrogen ions and produce carbonic acid. Well, the lungs take that a step further and create what's called an open buffering system, because the carbonic acid can, in the presence of a particular enzyme called carbonic anhydrase, can dissociate into CO2 and water, and the CO2 can be blown off or gotten rid of, breathed out in the lungs. So, under acidic conditions, the respiratory control centers will increase the ventilation rate, and that will cause CO2 to go down. We're going to blow off or breathe out more CO2 in the body, so we can think of this part of this series of reactions to go down or disappear, and that pulls the reactions to the left. So if we take away this product, that's going to essentially create a empty spot, which will drag these reactions to the left, and will use up some hydrogen ions, producing more carbonic acid. And so increasing ventilation rate increases pH, get rid of hydrogen ions. If we slow down the ventilation rate, which is what will happen if the pH rises, then CO2 will accumulate in the body. We won't be getting rid of it as fast. The cells are still making it at the same rate they were before. So CO2 accumulates, and the accumulation of something on the left side of these reactions drives the reactions to the right, and we produce more bicarbonate and more hydrogen ions. More hydrogen ions means a lower pH. So when things get acidic, ventilation rate goes up and corrects the pH. When things become alkaline, ventilation is reduced and corrects the pH. Again, we can't do that indefinitely. We can't just stop breathing in order to correct pH. We can't go around huffing and puffing all day long under the conditions of acidosis. So we have to have something else to take care of that This is just a restatement of the respiratory system responses. We have to have another thing to do to put everything right, put everything in the middle of its range of function. The kidneys are the ones that are going to really manage the pH situation in the long term. Under acidic conditions, the kidney tubules cells will add bicarbonate to the plasma. So now if you add a base, that's equivalent to getting rid of an acid or a hydrogen ion, we're going to be able to buffer those hydrogen ions as we add more bicarbonate, and that's what the kidneys do to handle this situation. There's two ways to deal with that problem, to solve that problem. One is to make sure that we don't pee out any bicarbonate ion when we're a little short on it. If we have a little excess acid and we need bicarbonate to neutralize that acid or to buffer it, last thing we want to do is let some bicarbonate get out of the body. So we're going to reabsorb all of the filtered bicarbonate. And then, if that's not quite enough, and that's usually the case, we have a positive balance of hydrogen ions being produced by digestion and metabolism, we're going to need to generate some brand new bicarbonate ions that can then neutralize or buffer those remaining hydrogen ions. There are cases in which we have alkalosis, and if we have those conditions that the kidneys need to compensate for, they can actually get rid of bicarbonate, secrete bicarbonate into the filtrate, and that's the equivalent to gaining hydrogen ions. So if we are basic or alkaline, that means we have a low hydrogen ion concentration. We can add hydrogen ions effectively by getting rid of bicarbonate from the body. Okay, so reabsorbing filtered bicarbonate. There are intercalated type A cells in the collecting ducts who can reabsorb bicarbonate, but then there's also other places bicarbonate can be reabsorbed in the nephron, but bicarbonate can't be reabsorbed directly, so it turns out there's a roundabout way to get the bicarbonate ions that have been filtered in the glomerulus back into the blood. Here's a diagrammatic illustration of that, and boy, does it look like a fancy mess of arrows and dotted lines and all kind of stuff. So let's take a look at this. It's not nearly as complicated as it looks. All we're doing here is taking the bicarbonate ions that were filtered in the glomerulus and reabsorbing them here and then into the blood. That's what all of this is about, is reabsorbing bicarbonate. The problem is we can't reabsorb the bicarbonate directly. There's not simply a carrier that can pump it across the membrane. What we've got to do is convert the bicarbonate ion by combining with hydrogen ions in the filtrate into carbonic acid, and then there's carbonic anhydrase enzyme present in the brush border of the proximal tubule cells and in the intercalated cells that can split the carbonic acid into water and CO2. The CO2 can diffuse into the tubule cell, and then once again we combine CO2 with water to form the carbonic acid right back again, and then let that dissociate into hydrogen ion and bicarbonate. So we've just effectively, if we could label this carbon, we would find that it's the same carbon that's now here in this bicarbonate. We've just moved it into the cell by this circuitous process, and now it can be transported into the blood. Incidentally, the hydrogen ion that's produced by dissociation of that carbonic acid will then be transported right back out into the filtrate to catch another bicarbonate ion. We continue this process until all of the filtered bicarbonate has been reabsorbed. There's a stepwise series of slides here that you can take a look at. First, we can produce that carbonic acid. Your authors have gone in a slightly different order than I have in discussing this. Then we can dissociate that carbonic acid and reabsorb the bicarbonate and secrete the hydrogen ions. And then we'll take the bicarbonate and the filtrate, combine it with the secreted acid, and produce CO2, which can be then absorbed into the cell and converted into carbonic acid. It's just kind of a cyclical process. It doesn't really matter where you start to talk about this loop. All right, so now we've reabsorbed all of the filtered bicarbonate. What about any additional hydrogen ions that we need to deal with, which again is typically the case? We need to generate some new bicarbonate ions to deal with it. One way to do that is to secrete hydrogen ions into the filtrate as long as there's hydrogen phosphate in the filtrate. We always have to have something to buffer the hydrogen ions that are secreted into the filtrate. We can't just keep pumping hydrogen ions in. The pH would plummet and that would burn various elements of the urinary system will be most bemused by that. So, pumping hydrogen ions in the presence of hydrogen phosphate. So as long as there's hydrogen phosphate in the filtrate, the intercalated cells can secrete hydrogen ions, and it will be buffered by that hydrogen phosphate producing dihydrogen phosphate, which can then be excreted in the urine. So now we've gotten rid of some more hydrogen ions. We're slowly cleaning up the hydrogen ion surfeit, and there may still be some extra hydrogen ions after we've already secreted hydrogen ions and allowed them to be buffered by hydrogen phosphate whilst reabsorbing the bicarbonate that we form. We may need to go one step further, and that is to create even more new bicarbonate. And in this case, we're talking about a chemical reaction where we're going to split glutamine, a common amino acid used as a building block for routinely for making protein. So there's always glutamine in the circulation. The proximal tubule cells particularly, but other cells in the nephron can take glutamine, break down glutamine to produce 2 new bicarbonate ions and 2 ammonium ions. So this is like a safe way to secrete hydrogen ions. NH3 can have an extra carrier on there, an extra hydrogen ion on there, forming ammonium ions, so that those can be excreted in the urine, and we've produced 2 brand new bicarbonate ions from this glutamine amino acid, which then can be absorbed into the blood. And we can keep doing this as needed until we neutralize the pH. And that's exactly what happens. Again, here we can see taking glutamine amino acids that come from the circulation, right? They come from the diet. We eat protein, we digest it, absorb the amino acids into the blood, take some glutamines and break them down into bicarbonate and ammonium ions. And we can transport the ammonium ions out into the filtrate to be excreted, and we can transport those brand new bicarbonate ions right into the blood plasma, and they will be able to buffer or neutralize the excess hydrogen ion that we had to deal with in the blood. So that's the magic of the intercalated cells and their ability to control or neutralize the net balance, positive balance of hydrogen ions each day. Again, as I said before, there could be a condition in which there is an alkalosis. We have insufficient hydrogen ions or a rising pH. In this case, the intercalated B cells, which is a different population of specialized cells in the collecting duct, will actually secrete bicarbonate ions into the filtrate, because getting rid of a base molecule is equivalent to creating or retaining a hydrogen ion. So we're low on hydrogen ions. We can essentially create some by secreting bicarbonate into the filtrate. Whoops, I jumped a couple of slides. I must have touched my mouse in a most unfortunate way. Here we are. So we were talking about secreting bicarbonate as the solution for an alkaline pH that needs to be remedied. We need to neutralize that condition as well. And these intercalated B cells handle that. All right, lastly, our last section is just a quick look at abnormalities, imbalances of pH or acid-base. There's 2 definitions or terms used to describe imbalances of this sort. If the imbalance is caused by some malfunction of the respiratory system, it's going to be called a respiratory acidosis or alkalosis, depending on which way the pH is going. And if any other problem causes the change in pH, the imbalance in pH, is going to be called a metabolic acidosis or alkalosis. So, in the case of a respiratory acidosis, the respiratory system is regulated. Now we're getting ahead of ourselves because we haven't talked about the respiratory system. The respiratory system is regulated so that there's a set amount of CO2 in the body, in the extracellular fluids, in the blood, in the arterial blood, I should say, not the extracellular fluids. The arterial blood should have 40 millimeters of mercury, what's called partial pressure. Just leave it alone for the moment. It's just a way of expressing the amount of CO2, and it's a pressure. So we're going to talk about it in terms of millimeters of mercury, but just think of that 40 number. That's the normal amount of CO2, and that's what the respiratory system is designed to maintain. If for some reason the CO2 rises above 45 millimeters of mercury, we'll have what's called a respiratory acidosis, if that's the initial problem. This could be caused by a decrease in ventilation rate. If we aren't breathing up to snuff and something, maybe there's a central nervous system depressant, and the respiratory centers aren't driving ventilation the way they should, CO2 will accumulate in the body and we'll have excess CO2, and that will lead to the production of hydrogen ions. As we'll review that a little bit. I think we will review that. We may not review that in a little bit. Let me just run back here and talk about really briefly these sets of reactions. If we have a respiratory malfunction where we're not able to exchange gases because we have a disease of the lungs like emphysema or pneumonia, or we have a depression of the central nervous system control of respiration, we're going to have an increase in CO2 in the arterial blood that's going to drive these reactions to the right, and we're going to produce some extra hydrogen ions. So decreasing ventilation will lower the pH, raise the hydrogen ion concentration. Let's go back to our discussion of a respiratory acidosis. So anything that impairs the ability of the respiratory system to get rid of CO2 as per normal will lead to a respiratory acidosis. If we have a extra hard-working respiratory system, we're breathing out, blowing off, it's often called extra CO2, then we're going to have a respiratory alkalosis. If you're hyperventilating, breathing more than the normal amount, meaning, very specifically, hyperventilation means to ventilate in such a way that the partial pressure of CO2 drops below 40 millimeters of mercury. Now we're going to have, we're going to blow off more CO2. We're going to have an alkalosis. We're going to draw those reactions we just saw to the left. We're going to use up hydrogen ions and bicarbonate ions and blow off more CO2. How about a metabolic acidosis? A metabolic acidosis is any other cause of an accumulation of hydrogen ions in the blood and extracellular fluids, not caused by the respiratory system. We're going to have an acid pH. What if we consume too much alcohol? There'll be potentially a small acidosis produced by acetic acid produced by metabolism of that ethanol in the liver. If we lose bicarbonate from the body, losing a base is like gaining an acid effectively. So diarrhea results in the inability of the colon, the large intestine, to reabsorb the last remaining amounts of bicarbonate that were added to the chyme in the digestive tract to neutralize stomach acid. So we've put some bicarbonate in there. We've got to reabsorb all of that bicarbonate, and we'll talk more about that in the digestive system chapter. Anyway, if we have persistent diarrhea, we're going to keep on losing that last bit of bicarbonate, and it's going to lead to an acidosis. Or if we have lactic acidosis, if we're in shock or we're exercising vigorously, or there's some tissue damage, some hypoxia, and the tissues are forced to do anaerobic respiration, we have a lot of lactic acid accumulating, we now have a metabolic acidosis. What if we have insufficient carbohydrates coming into the body, or insufficient access to those carbohydrates, those glucose molecules, by the cells because of insulin absence or insulin resistance, diabetes mellitus? That will also lead to an acidosis through ketone body production in the liver, as we mentioned before. So that's another example of a cause of metabolic acidosis. Metabolic alkalosis. What could cause too much bicarbonate in the body or not enough hydrogen ions? One possible cause of metabolic acidosis is the overingestion of antacids. This used to be a problem when the main treatment for esophageal reflux, heartburn, severe heartburn, potentially a disease state of heartburn, was treated by pouring bicarbonate ion containing salts into the esophagus so that it would neutralize any acid that had escaped out of the stomach and was causing irritation. And in severe cases, people would be taking a lot of bicarbonate and other bases to try to neutralize that acid, and that could cause a metabolic alkalosis. That's not so common anymore because we have newer types of drugs for treating GERD, which don't work on that principle. They work by preventing the acidification of the stomach, and so that we don't produce as much acid in the stomach and we'll see that other problems are caused by that. If we vomit out a lot of acid from the stomach, well, again, when we talk about the digestive tract, we'll find out that the way that we acidify the stomach contents is by splitting carbonic acid into bicarbonate ions, which go into the blood, and hydrogen ions, which go into the stomach. So if we spew out all those hydrogen ions from the stomach, then we're going to be left with all those extra bicarbonate ions in the blood, and we're going to have a metabolic alkalosis. Compensation. If we have an acidosis or alkalosis, whichever system has produced this problem, the other physiologic controller of pH will compensate, and we can take a look at the conditions of the body and identify an alkalosis or acidosis as being a respiratory or metabolic origin based on the appearance of the CO2 in the blood and the amount of bicarbonate ion. Okay, let me give you an example. Respiratory compensation. If we have a metabolic acidosis, we have an acidic pH of the blood. What will the lungs try to do? They will increase ventilation rate, and if you increase ventilation rate above normal in attempting to compensate for this pH problem, the partial pressure of CO2 is going to go down below what it normally would be. It should normally be 40 millimeters of mercury. So if we have an acid pH of the blood, and we observe that the partial pressure of CO2 is lower than normal, we know that this is a metabolic acidosis and that we're having a respiratory compensation. So just looking at the right variables, we can diagnose at least the class or the type of pH imbalance that we're dealing with. In a case of a metabolic alkalosis, the respiratory system will compensate by reducing the ventilation rate. We talked about metabolic alkalosis, so in this case we would have a decrease in ventilation rate, and if we decrease ventilation rate, CO2 levels increase, it accumulates in the blood, and this extra CO2 will drive the reactions that we saw to the right, producing more hydrogen ions, but at the same time we'll see this high PCO2, so we'll know if we measure an alkaline blood pH and we have a higher than normal PCO2 that we're dealing with respiratory compensation of a metabolic alkalosis. Renal compensation. You saw I snuck in a little statement at the bottom of these previous two states, which basically explains what renal compensation might look like. If we have a, whoops, I went the wrong way. If we have a respiratory acidosis, the kidneys are going to try to compensate by creating new bicarbonate. They're going to increase the amount of bicarbonate in the blood, and then the partial pressure of CO2 will be high. That's the definition of a respiratory acidosis. We have too much CO2 in the blood, and so that's going to drive the reactions to the right, producing the extra hydrogen ions. So in this case, we have an acidic blood pH and a high PCO2 instead of a low PCO2, and also there will be high levels of bicarbonate ion. So you can see that the PCO2 is going in the opposite direction with a respiratory acidosis as compared to a metabolic acidosis. Finally, renal compensation for a respiratory alkalosis. Again, this is not a long-lasting, long-term clinical problem. It's caused by hyperventilation typically, but the kidneys will respond by secreting or excreting more bicarbonate ion to try to right the ship, get the pH back where it should be. So we'll see a alkaline pH and a lower than normal partial pressure of CO2. So that way we can quickly diagnose the type of respiratory or pH imbalance that we see. All of the information about alkalosis and acidosis cases that we just talked about is sort of summed up in this table here. You can use that as a nice review to keep track of what causes each of those types of imbalances. The last slide, the very last slide in chapter 26, it's time to say farewell to this wonderful chapter that does so much just recollecting and reviewing stuff that we learned about in endocrine system, and in chapter 19 on the cardiovascular system. Well, we're ending with this last slide that talks about infants, and infants have the most vulnerable system in terms of maintaining their extracellular fluid volumes, their electrolyte concentrations, and their pH. So they're very susceptible to dehydration and pH imbalances. So in the first month of life, it's very important not to let babies get too much exposure to sun, for example, without sufficient fluid intake and so forth. So you've probably seen people taking extra care to shade and protect babies from hot environments, although they can adapt, and as long as we don't let things get out of control, they'll be fine. I know when my daughter was very, very small and we took her to daycare, after the first day in daycare, when we came to pick her up at the end of the day, the daycare manager came to us and said, so you have an air conditioner baby here, I see, because she wasn't used to being in a hot environment, and there was no air conditioning in the daycare center, and she was wilting. It was very funny. She had adapted to the very easy life of central air conditioning. Anyway, that's the end of our discussion for chapter 26. I do hope you'll join me as we go on. We're going to backtrack now and go back up and talk about the immune system next, and I'll see you then.